Hello, Geometer. It's Miss Backfish, and I am here to go over a review with you for our Unit 3, which is basically the right triangles unit. So this is everything right triangles, or maybe not everything, but many of the main things right triangles. And I can tell right now I'm going to need to work on focusing here 1 second so that it is not zooming in and out as I write. So hopefully that is going to be better. And we start when we're working with right triangles almost always with the Pythagorean theorem. Good old Pythagorean theorem. Pythagorean theorem, remember, is only true for right triangles. It's a relationship between the sides of the triangle, the side lengths. And very often what we do is we call them A, B, and C, and we say A squared plus B squared equals C squared. But I want to point out to you that something that you have to be very careful about with that is that C has to be the hypotenuse, or your longest side. The hypotenuse is the one across from the right angle, not where the two sides that meet at the right angle. The two sides that meet at the right angle are both called legs. So you have two legs that meet at the right angle, and then the hypotenuse is the one that we call C. And sometimes we use A, B, and C for sides of a triangle, and you don't even know if it's a right triangle, but you would still pick C for the largest side. So here we have C is our hypotenuse. Now, the reason I liked, well, where I'm going with this is that I like to not just say it this way, but also think of it as leg squared plus leg squared equals hypotenuse squared. Because a lot of times people get mixed up and they just think of it as, instead of the leg squared plus the leg squared, they say, oh, it's whatever two numbers I see squared. But that's not always the case. Like, for instance, in number 1 here, x and 3 are legs. 5 is the hypotenuse. So it's going to be x squared plus 3 squared that equals 5 squared. And so x squared plus 9 equals 25. Subtract 9 from both sides. And we get this, and we take the square root, and we get 4. Couple of things to mention there. The common error I'm talking about avoiding here by saying leg squared plus leg squared equals hypotenuse squared is people will look at this and just say, oh, okay, I'm going to do 3 squared plus 5 squared. In other words, the two numbers I know squared. But that's not how it works. It has to be the hypotenuse squared that's by itself on the other side. The other thing to point out here is when we take the square root of both sides of an equation, we usually put plus or minus. We're not doing that here because x is a length, and lengths can only be positive. Okay, so let's go on to the next one here. That's not the most vertical line I've ever drawn, but we will use it and move on. Here is another right triangle. 15 is the hypotenuse. These two are the legs. They meet at the right angle. That's how I know they're the legs. And this one's the hypotenuse. So leg squared plus leg squared equals hypotenuse. That's x squared plus 13 squared equals 15 squared. X squared plus 169 equals 225. Subtract 225 minus 169 and you get 56. Now, it didn't happen last time because 16 is a perfect square, so we didn't have to worry about how am I supposed to give my answer. But notice that this says both in simplified radical form, which we also call exact form, and as a decimal rounded to the nearest tenth. Okay? When you're asked to do something in simplified radical form, or when you're asked to give an answer in exact form, that means pretty much what exactly the easiest way to think of what it means is don't change it to a decimal. So if I do square root of 56, this type of calculator leaves that in simplified radical form for me, which is nice. Not every type of calculator does. Here's what happens if I do it on a different calculator. I get a decimal answer, which is great for decimal rounded to the nearest tenth. According to this, that's going to be 7.5. We haven't taken the square root here. That's where we're going with this. That's what I'm putting into my calculator is square root of 56. And so I'll say x is about 7.5. But I need the exact form as well here. And if this is the only kind of calculator I have, or any other one that does not simplify radicals for me, I need to know how to do that myself. So let's just look at that real quick. If you have something under the radical, and we're talking about square root. So if I had a perfect square under a radical, well, that can come out. That's ideal. So that's what I'd like to happen here. So what I'm going to do is I'm going to say, well, this is not a perfect square, but can I factor this number? Can I factor 56? Can I rewrite it as something times something where one of those is a perfect square? And yes, I can rewrite this as square root of 9 times square root of 7. Now, ideally, you want to do it so that you break it up with the biggest perfect square possible. In other words, what's the biggest perfect square that goes into 56? Be careful about goes into. If we say goes into, we mean as a factor, not like, oh, 49 is smaller than 56. No, that doesn't, 49 times something doesn't make 56. That's what I want. So the biggest perfect square that goes into 56 is 9. And then I can say, well, that comes out of the radical. Square root of 9 is 3. That's the goal, is to get things out from under the radical. You can't just take them out, though. You have to take the square root of a number to get it out. So that is the exact form answer for number 2, is 3 times the square root of 7, or sometimes we call that 3 root 7. Moving on. Number 3, finally, we have leg, and the missing is the hypotenuse. Okay, so this time leg squared plus leg squared is the two numbers squared and added that I've already have, the two that I see. And that's the danger, is that just, that's very, when we've been doing problems like this, boy, I'm tongue-tied today, sorry. The danger is just trying to square and add every two numbers we see. But like we saw over here, you're actually going to end up subtracting. We had to subtract the 9 from the 25. Here we had to subtract the 225 minus 169. On this one, we're not going to have to subtract. We have 36 plus 25. That's going to be what? 36 and 25. Why am I suddenly not capable of adding them? There we go. And take the square root of both sides to get x. All right. If you have one of these multi-view calculators, one nice thing about it is they can help you check when you're thinking, I don't think anything goes into 61. I think it's prime. Well, whether or not it's prime, there's definitely not a perfect square that goes into it. It cannot be simplified. If it can't be simplified, then what you're looking at is simplest radical form, or simplified radical form, or what we call exact form. Now, I wanted to show you, what if I have this type of calculator and I'm supposed to be trying to get a decimal? What do? Well, there are two places you can do it, but the easiest is probably right here. Just above the enter button, you have these two triangles pointing in opposite directions. There we go. And we have, this is about 7.8. And that's my answer. These are not the only calculators that have a button like that. There are certain other scientific calculators that do. Here we have a Casio that a lot of people like, that also has this button. And it's always those like two arrows pointing in opposite directions, like here, or above the enter button on this one, or right here. So if I have square root of 61, the lighting's a little bad over there, and I want to change it to a decimal, this button right here with the S and the double arrow pointing from S to D, well, it would help if I clicked it again. Come on. Actually, I think I have to press enter first and then change it. There we go. I'm not used to using this calculator. And there you have it. Okay? If you're not using one of those type of calculators, then you probably don't have that problem in the first place, because your calculator did change it to a decimal already. All right, a Pythagorean triple. What's a Pythagorean triple? Well, a Pythagorean triple is Pythagorean triple. Let's sort of define it informally. A set of 3 whole numbers which could represent the lengths of sides of a right triangle. It's kind of wordy, but that's trying to be as precise as possible. A set of 3 whole numbers which could represent the lengths of the sides of a right triangle. Key here is that they have to be whole numbers to be a Pythagorean triple. Do they have to be whole numbers to be the sides of a right triangle? Absolutely not. And the sides of a right triangle always work within the Pythagorean theorem. It always works for them. But basically, a Pythagorean triple, you can think of it as 3 whole numbers that work, so to speak, with the Pythagorean theorem. Like your most common one, 3, 4, and 5. And the reason, or to prove, I guess, it's a Pythagorean triple, 3 squared plus 4 squared is 9 plus 16. That's 25, which is 5 squared. In other words, this squared plus this squared equals this squared. Some other examples, 7, 24, and 25, 5, 12, 13, 6, 8, 10. There are quite a few. There are infinitely many, I guess. There's more than quite a few. Now, this is not saying those are the only possibilities for sides of a right triangle. Not at all. You can have any kind of sides of a right triangle. You don't have to have whole number sides. This is just saying these are kind of special. These are special circumstances. And we like them because who doesn't like to work with whole numbers? All right, next up we have, for each of the following, determine whether the 3 lengths given would form a right triangle. So reading carefully here, they specifically want me to know whether it's a right triangle. Look down here, number 8. This is worth noting. Number 8 asks a completely different question. It says, is it possible to form a triangle? And I put this to add this, I mean any triangle, with the following side lengths. 3 numbers can't always make a triangle. Let's say I have 3 lengths. I have 3 little sticks or something of these lengths. I have 3, and I have 5, and I have 10. 3 centimeters, 5 centimeters, and 10 centimeters are my sticks. Okay, and I want to try to make a triangle out of them. I can't, because if you tack one of them on one end of the 10, okay, let's put the 3 over here, and I tack one on the other end of the 10, there's no way, if they're tied to the ends of the 10, that they can reach each other and meet. So this can't make a triangle because it can't close. It can't touch each other. So that's what we're being asked in number 8. So let's look at that first. Very often in problems like these, the first question is, can it even be a triangle? So number 8 is asking, can it be a triangle? And on that one, it's not Pythagorean theorem based. It's just, can these 2 sides meet if they're attached at the end of this side? So that's the easiest way to think of it, is look at the 2 shorter sides, 4 and 8, and if I add them together, is that longer than the longest side? Is 4 plus 8 greater than 13? Nope, 12 is not greater than 13. It has to be literally greater, not equal. Equal is not fine. It has to be greater than. So these cannot make a triangle, because if I tried to attach 3 segments of those lengths, they just couldn't form a triangle. All right, up here, and we can check these first, even though we weren't asked. Is 7 plus 10 greater than 11? Yes. Okay, that's some sort of triangle. 5 plus 12, is that greater than 13? Yep. 6 plus 7, is that greater than 12? Yes. Okay, so all of those are triangles. It's just a question of what kind of triangle, and I circled right, but look, it says we form a right triangle, and actually it says an obtuse triangle or an acute. So this is asking me about all 3 of them. This is very often referred to as the Pythagorean converse, even though the Pythagorean converse is kind of more specific than this, but we usually use it to find obtuse and acute as well. Basically, the Pythagorean theorem says if you have a right triangle, then, like I start out with this knowledge, that means that the Pythagorean theorem applies. This relationship applies. Remember that a converse says, oh, it works the other way as well. In other words, if I have 3 lengths and this is true about them, then it must be a right triangle. So that's the Pythagorean converse. But it turns out we can actually use what we find as we're investigating this to determine more than that. Okay, so here's what I do. Remember that C is going to be your longest side. So I take the a squared and the b squared and I add them. Square the a, square the b, add those numbers together. Then I set that aside, set that number aside. I get some number here, whatever number, blah, blah, blah. All right, then I go over here and I think about c squared. Figure out what c is, I square it, and I have a number, blah, 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 over here. This is what I focus on to make my decision. I look at this number and I ask myself, compared back to that number that I set aside, is this bigger? Is it smaller? Or is it the same? Equal? Is the c squared bigger than this other number? Is the c squared smaller than this other number? So it's all based on c squared as compared to that thing that you did first and set aside. If c squared is bigger, it's obtuse. If c squared is smaller, that's acute. If c squared is the same, that's when you have a right triangle. That's the Pythagorean converse right there. You'll see a little bit more of what I mean as we do a few examples. And there's other ways to look at this, but I genuinely, strongly feel that this is the easiest way because when we think of obtuse and bigger, those seem similar. Those seem like they should go together. And smaller should go with acute. If you do it other ways, those you don't necessarily have that relationship. Okay, so here I've got A and B. I'm going to square them and add them together. And I take that number and I set it aside. Sometimes in a recipe, it'll say combine these things and then set them aside in a bowl. That's what I'm doing here. Then I go take my C and I square that. And this is what I make my decision on. Is this number smaller than the 149 I got, larger than the 149, or the same? It's smaller. So this is an acute triangle. Let's do it again. This time I'll label them the A, the B, the C. By the way, do check. Sometimes they'll be listed out of order. Don't just assume that the first two numbers are the smallest two numbers. Look for the two smallest numbers to be your A and B. All right, so A squared plus B squared. We're going to square and add 5 and 12. That gives me 25 plus 144. That's 169. I'm setting that aside to come back and compare to. C squared is 13 squared, which is 169. So looking at this, is it larger than what I got over here, smaller than what I got over here, or the same? It's the same. That makes it a right triangle because A squared plus B squared is the same as C squared. And finally, here we have A and B are 6 and 7 and C is 12. Again, don't assume they're in order. 6 and 7 are smaller than 12. So that's why that's my A and my B. A squared plus B squared. 6 squared plus 7 squared. 36 plus 49. That is 85. Yes, it is. Okay, 85. Then we have C squared is 12 squared, which is 144. So again, I'm looking at this number and saying, is this number bigger, smaller, or the same as this one I got earlier? It's bigger. That makes it obtuse. It's an obtuse triangle. And there we go. Moving on, the next big topic in our right triangles unit is special right triangles. Special right triangles. Wow, special. Why are certain right triangles special? Well, the ones we look at that we call special right triangles, and they're special really because they come up in so many contexts, and it's really helpful to know the relationship between the sides in terms of their ratio. For these particular ones are a 45, 45, 90, meaning it's a right triangle that has two legs that are the same. It's an isosceles right triangle, which means two base angles will also be the same. which means they both have to be 45. So if you have a right triangle that has two sides the same, then it's a 45, 45, 90. That's actually what we call them, 45, 45, 90. All right, when you are dealing with a 45, 45, 90, the rule is that the hypotenuse is always going to be whatever the leg is times square root of 2. Now, this is a leg, this is a leg. The legs are the two that are the same. So whatever one leg is, the other leg is as well. And this is not a complete lesson on this. This is just a refresher. So let's say that this is 6. Well, that means this is 6, which means that 6 times square root of 2 is going to give me my hypotenuse. So 6 root 2. Now, if I was going backwards from the hypotenuse, trying to get a leg, I would divide by square root of 2. So to go from the leg, either one, to the hypotenuse is times square root of 2. To go from the hypotenuse to the leg is divided by square root of 2. Another way I like to think about it is the only number you're going to use here is square root of 2. If you're going from the smaller to the bigger, you multiply by it. Bigger to the smaller, you divide by it. Remember, the hypotenuse is always your longest leg, your longest side, excuse me. Now, on this particular review, these three are the other type of special right triangles. So now that we've talked about 45, 45, 90, I'm going to jump down here. All right, this table is using this picture again and again with different values. So basically, every column is a new situation. Okay, so what's here does not relate back to what's over here. So first column, x is the leg. If the leg is 5, I'm going to multiply the leg times square root of 2 to get the hypotenuse. So y would be 5 root 2. All right, next problem. This time they gave me the hypotenuse. If I start with the hypotenuse, remember you divide by square root of 2 to get the leg. And dividing this by square root of 2 is the same as writing that over square root of 2, and that cancels. So the leg would be 4. You can also do it in your calculator. All right, next up we have, here's a leg that's square root of 2. Multiply that times square root of 2. I'm going from leg to the hypotenuse. This is the leg. This is the hypotenuse. So I'm getting larger, so I multiply by square root of 2. Square root of 2 times square root of 2 is just 2. If you don't believe me, ask your calculator. Here we start with the leg again. Leg times square root of 2 gets you the hypotenuse. So I can just write 9 root 2. I like to do that with the little arrows, that this leg to the hypotenuse is times square root of 2, and hypotenuse back to the leg is divided by square root of 2. What about this leg over here? It's exactly the same. And last but not least, if I start with the hypotenuse and I want to get the leg, I have to divide by square root of 2. Now, this case, it doesn't cancel like this one. I have 24. If I divide by square root of 2, looks like this. We're not allowed to leave radicals in the denominator. So what you have to do next is called rationalizing the denominator. Now, when I say have to do, I mean if you don't have a calculator that will do it for you. So I'm going to multiply on both top and bottom by square root of 2. And then what that gives me on top is 24 times square root of 2. And on the bottom, that just gives me a 2. And now I can simplify because 24 over 2 simplifies as 12 over 1. So this is just going to be 12 times the square root of 2. All right. Again, don't believe me, do it in your calculator. This is how I do it if I have to do it by hand. But you're not allowed to leave radicals in the denominator. So let's see how the calculator does the exact same thing. 24 divided by, and you could do it as a fraction or not as a fraction, square root of 2. And they get the same thing I did. 24 divided by square root of 2, not as a fraction. Same idea. All right, so that is my leg for the last problem. Okay, let's look at number 13 next because it's also about 45, 45, and 90s. Important thing to realize here is that this figure, the whole figure, is a square. When you take a square and you divide it down the middle just by drawing one diagonal, this is a diagonal, this part right here, then what you do is you just made two 45, 45, 90s. Notice over here, these little congruence markings, that's another way of showing you have a 45, 45, 90. Because, remember, it's an isosceles. Every isosceles right triangle is a 45, 45, 90, which means it has two congruent angles, and then it has a right angle. So that's another way to show you have a 45, 45, 90. Like you could have just those markings and not these congruence markings, or you could have just the congruence markings on the sides, or you could have the 45-degree angles. Whichever way you slice it, this one has a 45, 45, 90 triangle with a leg length of 14. So both of these are 14, and the hypotenuse is going to be leg times square root of 2. And that's 14 root 2. Now, let's look at 30, 60, 90s. That's our other type of special right triangle. So a 30, 60, 90 with a 45, 45, 90, you had to know one relationship. Okay, you had to know how to get from the leg to the hypotenuse. And even though you have three sides, you only had to know what number gets me back and forth from the leg to the hypotenuse, because you have two legs. Two of the sides that you have, 2 out of 3, are legs. They're the same. Here, though, you have 3 different sides. So we're going to name them 3 different things. Okay, a 30, 60, 90 is called that because you have a 90-degree angle, you have a 60-degree angle, and you have a 30-degree angle. We call the side across, or excuse me, the leg, remember legs meet at the right angle. The leg that is across from the 30, opposite the 30, so not next to it, not over here, but opposite it. We call this the short leg because it's going to be the shortest leg. We call this one the long leg because it's going to be the longer of the 2 legs. Remember, the longest side is always your hypotenuse, and the hypotenuse is exactly where it usually is, not touching the right angle, but across from it. Okay, the rule for 30, 60, 90s is generally starting from the short leg. And by generally, I pretty much mean always. We start from the short leg, whatever the short leg is, and I'm going to call it M, just for kicks. Whatever the short leg is, we can multiply that number times square root of 3 to get the long leg. So M times square root of 3 gives me my long leg. Okay, so I'm going to write this. Going from short leg to long leg, I always use a square root of 3. Okay, now why did I write it going both ways? Because to me, the easiest way to remember this is just what number gets me back and forth between them. And then in terms of what do I do with that number, think about whether you're going from a smaller side to a bigger side. If so, multiply, or a bigger side to a smaller side, then divide. So if I'm going from the short leg to the long leg, I multiply times square root of 3. Long leg to the short leg, I divide by square root of 3. All right, so that's the short leg and long leg. Then we also talk about the relationship between the short leg and the hypotenuse. And that has to do with 2. It's a 2-to-1 relationship. If I go from the short leg to the hypotenuse, I'm going to multiply by 2, which means if I go backwards, hypotenuse to short leg, I would divide by 2. So this would be 2m if my short leg is m. All right, so on these examples, I'm going to start with number 9. First thing I need to figure out is where is my short leg, where is my long leg, where's my hypotenuse? In this case, across from the 30, that's my short leg. So I'm starting with the short leg, which is where I like to start. Short leg times square root of 3 will give me the long leg. So 5 root 3 times square root of 3. That's going to be 5 times 3, which is 15. Use the calculator if you don't believe me. Short leg times 2 will give me the hypotenuse. So 5 root 3 times 2 is going to give me 10 root 3. So those are my answers for x and for y. That was what? Y. And this was x. Be careful about which is which. That's something I've been seeing my students get mixed up on quizzes. All right, next one. This time I'm starting with the hypotenuse. If you start with anything beside the short leg, since the rule is written from the standpoint of the short leg, always go to the short leg first. So remember that the short leg times 2 gives you the hypotenuse. So going back from the hypotenuse to the short leg, I divide by 2. So my short leg is x is going to be 8 divided by 2, which is 4. So there's my short leg. And then the short leg times square root of 3 gets me the long leg, which is y. So here's y. So x is 4 and y is 4 root 3. Last but not least, number 11 starts with the long leg. This is probably the messiest one to start with. If you're using the calculator that simplifies radicals for you, not so messy. So let's use that on this one. Remember, the relationship between long leg and short leg is square root of 3. So if I'm going from long to short, I'm getting smaller, so I will divide by that. So 18 divided by square root of 3. That's going to give me 6 root 3. So x is 6 root 3. That's my short leg. Then I have the short leg. The relationship between short leg and hypotenuse is a 2-to-1 relationship. Going from smaller to larger is what I'm doing here. I'm going to multiply by 2. So I'm going to multiply that number by 2. And I get 12 root 3 for the hypotenuse. So x is 6 root 3 on this one, and y is 12 root 3. And that is our quick review of special right triangles, and we're ready to jump into right triangle trig. Trig being short for trigonometry. Trigonometry actually literally means triangle measure. Nice root words to break down. Metry goes with metric, measurement, and trig is for triangle. All right, find the value of all 3 trig functions, sine, cosine, and tangent, for each of the acute angles in the triangle. Give your answers both as simplified fractions and as decimals rounded to 4 places. Sorry, I didn't give enough blanks there early. All right, notice that you do it for the acute angles only. We don't do sine, cosine, tangent of the right angle when we're looking at a triangle like this, okay? So first off, I'm looking at this triangle from the perspective of A. What I like to do is automatically go to figuring out what's opposite side, what's the adjacent side, and what's the hypotenuse side. Hypotenuse, Because remember, what I'm going to use, need a little bit more space here, I'm going to use SOHCAHTOA. I'm going to use these. This is just a way to remember the rules for the definition of the sine, the definition of the cosine, and the definition of the tangent. Those are right here. The sine of an angle. I'm going to use, I don't even know what I'm going to use. Sine of an angle, let's just do that, equals the opposite side over the hypotenuse. Those are the lengths. The length of the opposite side over the length of the hypotenuse, that's the ratio. That is the sine ratio. That's what it is. It's a ratio. It's a ratio with a name. The sine ratio. So that's why we have O over H here is opposite over hypotenuse. Then we have the cosine of your angle is the adjacent side length over the hypotenuse. That's what CA is for in SOHCAHTOA. CAH, cosine is adjacent over hypotenuse. And finally, we have the tangent of the angle is opposite over adjacent. So that's what TOA is about, that the tangent is the opposite over adjacent. All right, so I'm going to label this triangle looking at things from the standpoint of A. If this is my angle A, one way to think about it, if you ever get mixed up on whether to use sine, cosine, or tangent, if you ever get mixed up between the opposite side and the adjacent side, that's very likely what's happening if you're getting mixed up on which one to use. So here's how I like to do it. No fail way. If I'm using angle A has 2 sides, right? I'm going to trace them. These are my two sides. The two sides of the acute angle will always be the adjacent and the hypotenuse. Always. That means this is automatically the opposite. So which one of these is the hypotenuse? Well, that's here. So that means this one's the adjacent. Adjacent means next to, right? Both of these are next to A. It's just that one of them already has its own special name, the hypotenuse. So adjacent is the side next to your angle. The hypotenuse is the hypotenuse. And the opposite is the side that's across the triangle from your angle. All right, so the sine of A is going to be the opposite over the hypotenuse. That's what the O over the H means. So opposite here is 15. Hypotenuse is 17. So 15 over 17. The cosine of A is the adjacent over the hypotenuse. Adjacent over hypotenuse, A over H, 8 over 17. The tangent of A is the opposite over the adjacent. So that's 15 over 8. Now, I just did it as simplified fractions, but it says as decimals also rounded to 4 places. Be super careful here because there is a very common error here. When we pick up a calculator here, we want to hit the sine button or the cosine button or the tangent button. That's not what you do on this. This is the answer. The sine of A is 15/17. All we're doing if we change that to a decimal is literally changing 15/17 to a decimal. We don't want to do the sine of 15/17 because 15/17 is not my angle. We just want to change 15/17 to a decimal. Remember, on a calculator that's unlike this, if you want to change a fraction to a decimal, that's division. 15/17 just means 15 divided by 17. They said to 4 decimal places, so that's going to be 0.1, 2, 3, 4. Look at the next digit. The next digit, my fourth one is the 3. The next digit is the 5. 5 or higher goes up. So my 3 is going to change to a 4. So it's 0.8824. So this is approximately 0.8824. Okay, next up, 8/17. 8 over 17, change to a decimal, 0.4706. 0.4706. And last but not least, 15/8. 15 over 8 is 15 divided by 8. This one gave me a decimal right away, 1.875. I didn't have to round, which is why I wrote equals instead of approximately equal to. All right, now, here's the problem, is now I have labeled everything as if the only angle I care about is angle A, and now they're asking me about angle B. So what I like to do is I like to redraw the triangle. Okay, so I'm going to redraw this exact same triangle, just a quick sketch. Doesn't have to be perfect or beautiful. I just have to know what's across from what and what's next to what. All right, here it is. Okay, from B, this is my angle now. My angle has 2 sides. Those 2 sides are the adjacent and the hypotenuse. That means this is the opposite. Which one's the hypotenuse? The same as last time, 17. Here's the adjacent. Okay, so for sine of B, sine is opposite over hypotenuse, 8 over 17. Cosine of B, cosine is adjacent over hypotenuse. That's 15 over 17. And tan of B, tan is opposite over adjacent, so 8 over 15. All right, what I'd like you to notice here is that I already know what 8/17 is as a decimal because it's the same here and here. So that's 0.4706. I already know what 15/17 is as a decimal because it's right up here. So that's 0.8824. I don't know 8/15, so let's change that to a decimal. 8 over 15 is 0.53, repeating forever and always. 0.5333. All right, so very important relationship to observe, and I just kind of highlighted it, is remember that these two angles are considered the two acute angles of your right triangle, meaning they're the two that aren't right. They're smaller than that, they're acute, okay? Remember, another thing to remember about that is that these two angles in every right triangle will always add up to 90 degrees. If you're thinking, well, I thought it was supposed to add up to 180, that's all three angles. All three angles add up to 180. So if you know you already have 90, well, if I know they all have to add up to 180, whoa, take 90 out. What do you have left for the other two angles? You have 90 left. Okay, so these two angles always have to add up to 90. Keep that in mind. The sine of one of them every single time is going to be the same as the cosine of the other angle out of those two acute angles. The cosine of one of them every single time is the sine of the other one. And those two angles, remember, add up to 90. So another way we put that is that the sine of an angle is always equal to the cosine of its complement, the complementary angle. Remember, complementary angles add up to 90. What do I mean by that? Okay, let's say we have sine of 40. Well, what angle is complementary to 40? What would add up to 90 with 40? Well, that would be 50, right? So this is true. That's a very important relationship. Let's look at it in a triangle. If I had a right angle and then another angle was 40 and I subtracted from 90, I would get 50 here. Well, the sine of the 40 would be opposite from 40, would be across the triangle, would be right here. That would be the opposite of the 40. And then over hypotenuse, right? So for the 40, this is the opposite, and this is the hypotenuse. What about for the 50, though? Well, for the 50, this is now the adjacent, and this is the hypotenuse. So yeah, it makes sense that you get the same thing because opposite and adjacent just switched. If that's something you need to know more about, I suggest another video. We need to move on. Now what we're doing is we are using this to find missing side lengths and missing angle measures. All right, so number 15, find the value of x to the nearest tenth. We always start the same way, figuring out which angle we're going to use. One side of the angle is the adjacent and the other side is the hypotenuse. Remember, the hypotenuse is the side that does not touch the right angle. That makes this the opposite. Be very careful. I do have another video on identifying opposite and adjacent and hypotenuse. If you are getting mixed up on which one to use, you probably are having trouble with that and need to go back and work on it. Okay, so I'm not working with the hypotenuse at all in this problem. It's not a side that I know, like this one, and it's not the side that I need, like this one. So I'm going to work with the one that I know and the one that I need. So I'm working with opposite and adjacent. Okay? Remember our good friend, let's write him up here, SOHCAHTOA. That helps me remember which one is which relationship is opposite and adjacent. Well, it's the tangent. The T stands for tangent. Tangent is opposite over adjacent. So I'm going to write an equation. And my equation is basically the definition of tangent. Tangent of my angle, in this case my angle is 50 degrees, equals opposite over adjacent. The way I like to do this is always cross multiply next. So I put this over 1 and then I cross multiply. X times tan 50 equals 13 times 1. Is X alone? If X is alone, then I'm ready to put things in my calculator. If X is not alone, I need to get it alone. That's what solving is all about. Isolating the variable. All right. I divided out this because it was X times tan 50. So to get rid of the tan 50, I have to divide by tan 50. Now X is alone. And the other side tells me what goes in the calculator. So it's 13 divided by tan 50. If you have ever asked yourself why on some of these do I multiply and some of them I divide, and how am I supposed to know which is which? This is how you know. You go through the process of cross multiplying and getting x alone, and then whatever it tells you to do is what you do. I could have done it as a fraction instead. If that would make you feel better, go for it. I get the same thing either way. So x is, and for side lengths, it doesn't say, does it? Yes, it does, to 10th. That's a pretty common thing. Side lengths, it's very common to round to the nearest 10th, but always check. They might want the 100th place. X is about 10.9. All right, next up, number 16. Once again, we're finding a missing side. I'm going to go with the angle that they've given me. I'm going to label things from that perspective. Okay, we have 5043, has two sides. One of them is the adjacent, and one of them is the hypotenuse. Okay, that makes 36 our opposite side. Okay, so those are the names of the sides with respect to this 43-degree angle. So it looks like, again, I'm working with opposite and adjacent. I don't have any need of the hypotenuse. It's not the one that I was given. It's not the one that I need. All right, so I'm working with opposite and adjacent. O and A, TOA. Tangent is equal to the opposite of over the adjacent. So tangent of my angle equals the opposite over the adjacent. This is a very similar problem, actually. Let's cross multiply. It's like this is over 1. X times tan 43 equals 36 times 1. Divide both sides by tan 43. And now X is alone, and that tells me what to put in the calculator. So 36 divided by tan 43 gives me 38.6. So X is 38.6. All right, number 17. Find the value of X. Still trying to find the value of a side length. Okay, so here's the angle I'm working with. It has two sides, and those are always going to be your hypotenuse and your adjacent. Which one's the hypotenuse? This one. So this is the adjacent. So that makes this side the opposite, and this time it's the opposite that we're not actually using at all. So I need to work with the adjacent and the hypotenuse. That's A and H. That's ka for our little SOHCAHTOA. Cosine is the adjacent over hypotenuse. All right, so I'm going to do a cosine equation. Cosine of 15 degrees equals adjacent over hypotenuse. Now I'm going to cross multiply. 50 times cosine 15 equals x. Is x alone? Why, boy, howdy, it sure is. That means I don't have to divide. I get to multiply this time. This tells me x, to find x, you need to multiply 50 times cosine 15. What am I going to do? When you have an angle like 15, 30, 60, 45, sometimes your calculator will try to give you an answer in exact form. Remember, we have a button down here that changes that to a decimal. So that's all we need to do is press that button, and it will give me the decimal. So 48.29 becomes 0.3 is approximate value of my missing side. All right, number 18. Find the missing angle. Now we've moved on to finding missing angles instead of finding missing sides. All right. The nice thing about this, or the thing to know about this, is that we start out by setting it up exactly the same way as when we were finding the missing side. So I'm going to call this, I don't like question mark, I'm going to call it theta. What is theta? Theta is a Greek letter that we use an awful lot to stand for a missing angle. It's just like a variable. It's just like if I used x. Okay, so I'm going to use this because we do that a lot. We use it a lot for angles. So this is my missing angle now. I'll do the same thing over here. Instead of question mark or X, I'll just call it theta. All right, it's just a letter. Don't get wigged out by it. So here's my angle. Remember, my angle has two sides. One's the hypotenuse and one's the adjacent. So that seems to be the two sides I'm working with here. 15 is the hypotenuse. 9 is the adjacent. If I'm using hypotenuse and adjacent, H and A, that's cosine. Cosine is adjacent over hypotenuse. So the cosine of theta will give me the adjacent over the hypotenuse. Again, you could have just as easily called this x. Cosine of x equals 9 over 15. Nothing particularly special about the theta. Now, here's what's special is this is not cosine times theta. These are not separate. They're not detached. Everything we've done, if you look at this, when we move things around, it moves all as one unit. Okay? So that cosine's attached to that theta. How do I get it detached? I do the inverse cosine. So I'm going to do the inverse cosine of both sides. You don't usually show this step. But what happens is, if I do inverse cosine, it moves it to the other side, and I say, I'm going to do the inverse cosine of 9/15. In other words, if the cosine of my angle is 9/15, then the inverse cosine of 9/15 will give me the angle. It's like working backwards. It's like asking the calculator, what angle gave you this cosine value? All right, so inverse cosine, you press the second button to go up above cosine, and it gives you that little -1 thing. It's not cosine to the -1 power. The -1 is just notation. It's just inverse cosine. And then 9/15. That's the same as 9 divided by 15, and I get 53.13. Be careful if you're using a graphing calculator. Okay? It needs to be in degrees. For everything we're doing here, it needs to be in degrees. I pressed mode, and then I checked. If this was not in degrees, I would arrow down and I would change it from radians to degrees. This one's in degrees, we're good. So it turns out that the angle that gives you a cosine of 9/15 is 53 degrees. A lot of times for these, you round to the nearest whole degree. So my angle is about 53 degrees. Next up, what do you know? Cosine again. That was not intentional on my part, but this is the adjacent, and this is the hypotenuse, so we will use the cosine yet again. Cosine of theta equals 3/7, which means theta, my angle, will be the inverse cosine of 3/7. So this time I'm going to use a different calculator. Inverse cosine. Only use the inverse when you're looking for a missing angle. That's the only time we use the inverse. That's the only time we hit that second button, is looking for the missing angle. Please don't get inverse button happy. Very often that's what happens. Once we learn to do inverse, students start thinking, oh, okay, I guess I need to press this every time. You do not. Only for the missing angle. 64.6 degrees. That rounds to 65 degrees if I need a whole number angle. Next up, well, this doesn't have a picture. It just tells me the tangent of my angle is this. Well, that's kind of like skipping down to this step. They've given me the equation. So if the tan of my angle is blah, 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 then the inverse tan of the blah, blah, blah will give me the angle. In other words, I can think of this as, let's look at it like this. This is another way to look at this. It's kind of like saying, I want to move this tan away from the angle, but if I do that, it has to be an inverse tan. That's not really the mathematical way of thinking of it, but that's one way you can think of it. It's kind of like if you move it to the other side, you make it the inverse. So I'm going to put that in my calculator. On this kind of calculator, the second button is actually a shift button. It's always pretty much in the same place though. So I'm going to do shift tan, and you see that it gives you what you're looking for. It gives you that little inverse tan. And then I'm going to type in 2.475. And I was about to say, and then it goes away. No, it gives me 68 degrees. There we go. So what does this mean? This means if I were to take the tangent of 68 degrees, I should get something close to 2.475, and I do. Why is it not exactly the same? Well, because we're rounding. We rounded to get this 68. So it's going to be close, but not exact. All right, and last page here is we are doing more of using what we just went over, finding missing side lengths, finding missing angles, to, in this case, solve for 19, solve the triangle, and for number 20, to solve an application problem. Solving a triangle means find all missing sides and angles. Okay, you got to do them at one at a time, though. You can't solve them all at once. You can't find all the missing sides and angles at once. So let's see what's missing in this first one. We are missing, we don't know the hypotenuse. We don't know this acute angle measure, and we don't know this acute angle measure. Okay, those are the three things I'm going to find. And when you're asked to solve, almost always that's what you got, is you're missing three things. I think the easiest thing to find first would be the hypotenuse, because I know 2 out of 3 sides. If you know 2 out of 3 sides, you can use the Pythagorean theorem. So 40 squared plus 18 squared. Leg squared plus leg squared equals hypotenuse squared. So this is my hypotenuse squared. So if my hypotenuse squared, which is what, AB, if AB squared is 1924, then AB is going to be the square root of that. So let's see what we get for that. 43.86. When we are solving right triangles, we generally go ahead and do decimal values. And so I'm going to do, for all of these, I'm going to do side lengths to the nearest tenth and angles to the whole degree, whole number degree, or the nearest degree. So I'm getting AB is about 43.9. All right, so that's this. Now, since I now have all three sides, I could use sine, I could use cosine, I could use tangent to find any of these missing angles. But I like to always stick with going for using the ones they've given me, because you're going to be more accurate that way. This answer has already been rounded, so it's already less accurate than 40 exactly or 18 exactly. So I'm not going to do any more, I'm not going to lean any of my additional work on this number that I did. I'm going to go ahead and continue to use these two sides. You get to pick whether to find angle A or angle B first. It's completely up to you. Fair warning, I'm afraid this video may cut off soon, and if it does, I will give you a little amendment video, but I'm afraid, I don't know, it's doing funky things. Okay, I'm going to find A. You could have chosen B. I'm going to choose A. So angle A, here is opposite from angle A, and here is the adjacent from angle A. So I'm going to use the tangent. Tangent of angle A equals opposite over adjacent. That means that angle A is the inverse tan of that same fraction, 18 over 40. And that's what goes in my calculator. Inverse tan of 18 over 40. You could do it as division. It doesn't have to be as a fraction. Well, 24.22. So that rounds to the nearest whole degree. That's 24 degrees. All right. And then the beautiful thing here is that I don't have to do tan, sine, cosine, or anything with it more than once. If I know one of the acute angles, remember that the two acute angles always add up to 90 in a right triangle. So all I have to do now is do 90 minus 24 to get the other angle. And I got 66. And now I have all three of the missing things I was trying to find. All right, I think this video may cut off at an hour. So let's see if that happens. We are almost there. Can you believe it? Adjacent is here. Hypotenuse is here. I'm going to find this x. That's what I'm going to find first, because x kind of attracts me to it, and I want to do that. So this is cosine. Adjacent and hypotenuse is cosine. So cosine of 39 degrees equals adjacent over hypotenuse. Cross multiplying gives me this. And is x alone? Yes, it is. So I'm ready to put it in my calculator. There it is. X is 10.10, so 10.1. All right, so I found one of my missing pieces, puzzle pieces. This is 10.1. All right, am I going to have to use an inverse function in this one? That's a big no. The only time you have to use an inverse function is when you're finding a missing angle, and the only reason that you would need to do that is if you don't know either of these two acute angles. If you know one of them, remember to find the other one. We can just take that one and subtract it from 90. And I get 51 degrees. All right, last but not least, finding side RS. We could do this a few different ways. Personal preference, I think I would probably, this is maybe, I don't know. I go back and forth. I tend to get lazy at this point and do, maybe it's not lazy, but I tend to say, I'm just going to do the Pythagorean Theorem because I know 2 sides out of 3. But that kind of breaks my own rule of not using a side I came up with. So sometimes what I'll do to make that a little better is, remember down here when I did 13 times cosine 39 and got 10.1? I'll leave it in the calculator and say, okay, now I'm going to do x squared plus, calling it, I don't want to call that x, I'm sorry. Let's call this y. Y squared plus this thing squared. So let's square it. All of that, 102, blah, 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 equals 13 squared, which is 169. That's y squared plus this squared equals 13 squared. I'm leaving it in my calculator to leave it as accurate as possible here. And then I'm going to subtract this number from both sides. So 169 minus that number gives me 69 point blah, blah, blah. So y squared equals 66.93, blah, 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 blah. And then I'm going to take the square root of that. Oops, I hit the wrong button. Okay. And I get 8.18. So that's about 8.2. That is probably just as accurate as you would be if you did it what I would consider the most accurate way, which would probably be to continue using 39 and 13 and say, okay, here's the opposite. Here's the hypotenuse. I'm going to use sine. So let's do that real quick. Sine of 39 equals opposite, which is y, over hypotenuse, which is 13. 13 times sine of 39 equals y. This is not really a longer way or anything. It's pretty quick. 13 times sine of 39. 8.18. That's how I got here from the other one. So it's very close. So those are my 3 missing items. QR, RS, and angle S. All right, last problem on the review. Can you believe you've waited this long? When the angle of elevation of the sun is 63 degrees, let's remember that angles of elevation are always above horizontal, because sometimes you're not shown in the picture where it is. And angles of depression are always angle of depression underneath the horizontal. But they're always with the horizontal as one side. You always have a horizontal line as one side of that angle. So if you're looking at your right triangle and you're trying to figure out where the angle of elevation or angle of depression would be, keep in mind it's got to be where the horizontal side is. So right there. This one's not either one, it's the right angle. So the tree casts a shadow that is 27 feet long. And again, this time it's given to me on the picture, but don't ever forget, when it talks about a shadow, that's always going to be the part on the ground, because that's where we see our shadow, is lying on the ground. To the nearest foot, how tall is the tree? So what they want from me is they want this part. So I'm going to redraw this triangle without all of the extra business on it and say I've got 27 here, I've got 63 here, and I want this height. All right, well, Now I'm just finding a missing side length. So let's use the angle they gave us and figure out, well, that's the hypotenuse. Remember, the two sides are the hypotenuse and the adjacent. So this is the adjacent. This is the opposite. So what am I working with here? I'm working with the opposite and the adjacent. That's tangent. Tan of my angle equals opposite over adjacent. 27 times tan 63 equals h. Go to my calculator because h is alone. That means it's time to put it in the calculator. 27 times tan 63. 52.99. I'm going to go ahead and round that to the nearest foot. So 52.99 becomes 53 feet. And we are done. Longer than I wanted, but hey, we got it done and we hit everything. So I hope this has helped you. I can't wait to see how awesome you do on your test. Let me know if you have any questions, and I'll talk to you later. Bye-bye.